Hello and welcome back. Let's take a look at another example that involves work. In example 3, we have a 100-pound rope that's 40 feet long and hangs vertically from the top of building 61. How much work is required to lift the rope to the top of the building? And I've drawn a little picture there below. So here we have the 100-pound rope. It's 40 feet long. And the issue here is that the force that we have to overcome is a constant. That's gravity that we're trying to overcome in pulling up the rope. So that's a constant for all the pieces, all the parts of the rope. The thing that's changing here in our work computation is the distance that each piece has to travel. You can imagine, like, back to the work equals force times distance. When we looked at Hooke's law, it was force that was changing as x changes. But in this case, it's the distance itself that is changing for each little piece of the rope. That distance is no longer a constant for our entire object here that we're moving. So how can we handle this? Well, what we could do is set up a little number line to represent, to lay the rope down on. And so I'm going to draw a number line here. I'm going to make it so that we'll call this y, because it's kind of like a vertical number line. And I'm going to make it so that y increases as you go down. It's a little bit strange at first, but you'll see why in a moment. No pun intended. Okay, maybe a little bit intended. So here we have the rope. This is going to be 40, y equals 40. And at the top it's y equals 0. So here what we could do is, actually I'll just explain, I guess, why increasing going down. Well, here y can represent the distance that each little piece of the rope has to travel to get to the top of the building. So here, if y is equal to 40, where you're at the bottom of the rope, then that bottom piece of the rope has to travel a distance of 40 feet to get to the top. And the top of the rope here just travels a distance of 0. And you get all kinds of distances for everything in between. So what we're going to do is take that interval from y equals 0 to y equals 40, chop it up into a bunch of subintervals. Sorry, I have the sniffles, but the video must go on. Can't wait for the sniffles to stop. And I'm actually going to draw another copy of the rope over here to the right. So there's the rope going from y equals 0 to y equals 40. And what we're going to do is take just a little piece of it. So we have this little interval representing this little piece of the rope. Now, when you think about this piece, there's like a top of the piece and the bottom of the piece. And so those have to move different distances, when you're pulling them to the top. But here we're just going to assume that the entire piece has to move one constant distance. Now the piece length is going to be delta y, and the y value that this piece length is at we'll call y sub I. So this piece has to move a distance of y sub I to get to the top. That's what we're saying here. Now that's an approximation, right? The top part of the rope doesn't have to move as far, so there's actually less work involved when we use y sub I as our calculation for the whole piece. But this is just an approximation, or is going to be an approximation, for the work that's performed in lifting this little piece of the rope up to the top. So let's figure out off to the side here what force we're going to have to overcome to lift this piece all the way up to the top. And the force we're having to overcome is gravity. So the way to figure out that force is to figure out how heavy this little piece is. Now we know that the entire rope is 100 pounds for the entire 40-foot length of the rope. And one of the things that's going to be useful here is to figure out the linear density, so how many pounds per foot. But we can do that by taking the 100 pounds and dividing it by 40 feet. And that fraction represents the number of pounds per foot for any part of the rope. That would be the linear density right there. And maybe I'll just mention this off to the side. This is the linear density. So this is the number of pounds per foot. Then we're going to multiply that by the number of feet in length that this little piece is. And it looks like we said it was delta y. So this is like delta y feet. And I'll put this over 1 just so we have like fractions to multiply together. So what we get is 2.5 delta y. Notice that the units of feet cancel and we just get pounds. So 2.5 delta y pounds of force to lift this up. That's how heavy, in other words, that little piece is. Now we're going to use that force to figure out how much work there is done in lifting the piece up to the top. Here, work is going to be the force times the distance to the top, and the distance to the top is going to be y sub I. So because we said that this little piece is at a y value of y sub I, and remember that the way we set it up, y represents, nicely at least, represents the distance traveled to the top. So now we can fill in f sub I, that's 2.5 delta y, and then we have a little y sub I. Usually it's nice to put the delta y off to the right, because the next step is going to be to sum up all these little works. This part that we just figured out is the work that's done to move that little piece up to the top of the rope. Let me write that out. There we go. Now the actual work to lift, so we're going to add up all these little works. Now the actual work to lift up the rope is going to be the limit as n goes to infinity of the sum of all those little works. Now n here is the number of subintervals that we chopped up our interval from y equals 0 to y equals 40 into. And as the number of subintervals goes to infinity, these intervals get smaller and smaller, so you're looking at smaller and smaller pieces of the rope until you're thinking about just moving one infinitesimally small cross-section of the rope and lifting it up to the top. So you're just chopping this up into tiny, tiny little pieces. These approximations get better the smaller the pieces you have, because there's less difference in the distance that that piece has to travel as you move from the top of the piece to the bottom of the piece. So this is going to be the limit as n approaches infinity of, here we've got 2.5 y sub I delta y. But we know that this is the definition of the definite integral. This is going to turn into the integral of 2.5 y dy. And the y values are going to go across the rope. They're going to go from 0 to 40. Just going across the rope. All right, so then if you figure this out, you'll get 1.25 y squared from 0 to 40. And this should give you 2,000. And the units here, since everything's in British units, pounds and feet, we have 2,000 foot-pounds. Okay, so that's example 3. In the next part, we'll take a look at example 4. See you there.